This is a video key for our required review for chapters 1 through 5. You'll notice that I did show you the midterm 1 memory aids that you will get for the exam. You can print off this exact page. It's on the exam, so you can print it off before you take the exam. Make sure you print it before the exam because you can't print anything once you're logged into Proctorio. Okay. Number 1, a study was done to see whether a 100 milligram caffeine pill taken each morning before class can improve the performance of a student on a statistics exam. Suppose all students in the 8:30 class are given caffeine, all students in 9:30 can't have any caffeine. Later, they compare their scores from the midterm. So first, is this a controlled experiment or an observational study? So I've written some notes in already to save time. The biggest difference between a controlled experiment and an observational study is in a controlled experiment, the researchers decide who gets what treatment. Now that can still be double blind because they just say like, okay, we need one group that has this, we have one group that does this, we give someone a treatment, we can randomly assign people, we can choose who goes in each group. But basically, whether they actually know for sure which person's in each group, they set up the groups, they set up the treatments. Okay, so let's look at this. So when we look at this one, it does look like the researchers would choose to give caffeine to the 8:30. They chose a control group. So this would be a controlled experiment. Okay, but we have to also tell them why. Okay. It says an observational study because the subjects were not randomized. Well, it is true. This is true that they were not randomized, but that's not actually what makes it controlled or not. So it's not going to be that one. An observational study because there's no control group. Well, in this case, there actually is a control group. So it's not going to be that either, but even if there wasn't a control group, that's not the deciding factor. The deciding factor is researchers decide who gets the treatment. Okay, 3, an experiment because the caffeine pill was imposed. When they say it was imposed, that means they give the caffeine to someone, so that means they're giving it to people. They decide who gets the treatment. Okay. Let's see, define the treatment and control group. So treatment would be whoever took the caffeine, the control group is the class who didn't take it. So it looks like I matches that. The response variable is always what you're measuring, so they're comparing their scores from the midterm. So it looks like the response variable would be exam scores. The treatment variable, or the explanatory variable, that's what you're trying to use to explain it, and we're trying to use the caffeine or not caffeine to explain how well they do. So the explanatory variable is the caffeine pill. Okay, is the study randomized? Okay. Well, I would say no, because only the 8:30 a.m. students were given the pill. Students aren't necessarily usually randomly placed into time slots. So I would say, again, no, because you only give to one specific block of students and instead of trying to randomly assign them in there. Okay, is the study blind? Well, here's our note. Blind means that the subjects don't know which group they're in, and double blind means neither the subjects or researchers know. Well, going back to look at the original thing, it says 8:30 a.m. has a caffeine pill, 9:30 a.m. they can't have any caffeine. I think it'd be pretty obvious to the students whether or not they're getting a caffeine pill or they just can't have caffeine. So it can't be blind, and if it's not blind, it's not going to be double blind. So I would say no, because there's no placebo. You would have needed to give some of the students a caffeine pill and some of the students a placebo pill, and then they wouldn't know which one they were in. It turns out there's a different teacher for the 8:30 a.m. section than 9:30. Maybe the difference in the two sections was just due to the different teacher. This would be an example of a confounding variable. So remember, a confounding variable is some other variable that we're not accounting for that's affecting your response variable. So the instructor being good or not good would affect the exam score. So that's a confounding variable that wasn't part of our study. Group 2, or problem 2. John has 5 tomatoes here on the left. Everything's to the same scale. He just got 3 more tomatoes, X, Y, and Z, and tomatoes X, Y, and Z have weight equal to the average of this group. So basically, he had these 5 already. He found the average, and X, Y, and Z all have that same weight as the average. So if we add them all together and get a group of 8, what will happen to the average? Well, you had big and small ones over here, but X, Y, and Z, they're all already equal to the average, so should the average change? Not really. So the average is going to be about the same, because again, they're just equal to the average. When it comes time, though, to compare the standard deviation, what's going to happen? So remember, standard deviation measures how far you are from the average. So that's the whole goal of standard deviation, tell you how far you are from the average. And so for these 3 tomatoes, they have deviations of 0 from the average because they are equal to the average. So when you subtract them from the average, you're going to get 0. And so over here, you had some big, you had some small, you had range, but X, Y, and Z, they're really close to the average. So it's kind of making it so your data overall is more condensed and closer to the average. So your standard deviation would be smaller. Now that is a problem that we're just kind of using a little bit more logic on. There's not really new formulas or anything specific we've learned, just some logic. Guinea pigs were injected with a bacterial infection in a medical study, and the number of days they survived were recorded. This histogram shows the percent of their survival times in days. The intervals for the number of days include the left endpoint, but not the right. So first thing we're going to do is try and label the axes. This is something that will be on the exam. So for the horizontal axis, this is the days that they survived. So it's survival time in days, days being the important unit here. So what's the correct label for the horizontal axis? It would be days. What's the correct label for the vertical axis? Well, this is the part you have to memorize. It is always percent per whatever your unit is for your horizontal. So our unit was days, so it has to be percent per days. Is the shape of the histogram for the above data, is it long right tail, long left tail, symmetric, is it normal like a bell curve? Well, if I was to kind of draw it in, it looks like it would have a long right tail. Next one, based on the histogram, which interval is more crowded? So when we say crowded in this situation, we kind of mean, if you were to think of it as like a bunch of people that are stuck in this category, which category would be more crowded? So when I look at this, here's 80 to 100 or 100 to 110. It looks like they crammed a lot more people into this 80 to 100 because it's higher. So they kept cramming in the people and they had to go higher and higher to have a place to sit. So whenever you ask more crowded, we really mean which one is taller. Which in our case is 80 to 100. Next, approximately what number of days is the median? So remember, your median will have 50% to the left and 50% to the right. So what you have to do for this is you have to find the percentages for each blocks and kind of add them up to see where 50% would be. To keep myself organized, I'm going to do this little table. This isn't a table you have to memorize. I don't think I've done it in the lectures. Just to keep me organized. So my first category goes from 40 to 60. Let's find our percent. So remember, percent is equal to your width times your height. So from 40 to 60, that's a width of 20 and a height of 0.75. So 20 times 0.75 equals 15%. So this block right here has an area of 15%. My next category is 60 to 80. It also has a width of 20 and a height of 0.75, so that's 15%. And then, let's see, my next category is 80 to 100. Let's see, 80 to 100, that looks like a width of 20 and a height of 1.7, which gives me 34%. Now, I've been forgetting to add them each up. So my first interval, I only have one, so 15%. But next one, I'm going to have 15 plus 15, which equals 30%. So I'm still not up to 50 yet. I'm trying to get to 50. My next one, I'm going to add that again. So 15 plus 15 plus 34, which gives me 64%. So this is bigger than 50%. This is smaller than 50%. So where's 50%? Somewhere right here in the middle. So the median is going to be between 80 and 100, because of somewhere at 80, we're at 30%. At 100, we're at 64%. So it has to be somewhere there in the middle. So let's go with number 2. Let's see, according to the histogram, what percent of the guinea pigs died on day 200? So for any time I ask you for a specific day or specific year or whatever it is that you're doing with your histogram, the percent for that specific thing is always just going to be the height, because remember this is percent per day. So on day 200, the percent on day 200 is 0.1, so 0.1%. Let's see. And from the histogram, the average number of days of survival must be, it looks like we're comparing it to the median. So it should be bigger or smaller than the median. Well, this has a long right tail. So if my median is right here, the long right tail will always pull the average. So my average is going to be somewhere higher. Probably not at this high, but I ran out of room to write. So a long right tail will always pull your average over. So our average should be bigger. That would be I here. Number 4, suppose the distribution of math SAT scores from Utah this year is normally distributed with an average of 483 and a standard deviation of 100 for the males. So normally distributed, that means we're talking about things from chapter 5. We're going to have an average of 483 and an SD of 100. Let's see. Someone who scores 780 or higher on the math SAT can be considered a genius. What is the percentage of male geniuses among the male SAT takers? Okay, so to start with, I say, okay, I have my number of 780. I'm looking for the area to the right. I'm looking for the percentage of people who scored higher than that. But I don't have a table that lets me look up 780. So what I have to do is I have to standardize. Z equals X minus the average over the SD. So in our case, our X we're interested in is 780. So 780 minus 483 over standard deviation of 100. This gives me 2.97. And I draw my picture. So here I had 780, but I've rescaled it to my standard units. So Z is equal to 2.97. And I want this area to the right. So I'm going to pull up my normal table. And I look for 2.97. It looks like I'm at 2.95 or 3.0. I say just pick the closest one. I'm not going to try and make you find averages or extrapolate somehow. So it looks like this area is 99.84. But wait, that doesn't seem quite right. That's my area to the left, and I wanted the area to the right. So I'm going to come back to my picture. I always think pictures make it better. The area to the left is 99.84%. Well, how do we go from the area to the left to area to the right? Remember, all areas have to add up to 100%. They always do. So we'll do 100% minus 99.84%, which gives me 0.16%. Now, on your exam, the department person who wrote the exam uses a calculator, and she might also round differently. So our answers aren't going to be exactly the same. So we're going to want to pick the closest one. So 0.16%, that's really close to 0.2. You'll often see a little bit of rounding because they just want to make sure that all the different students who might round differently get to the same result. So just kind of pick the closest answer. Okay. The percentage of male SAT takers who score between 283 and 683 is about what? Okay, so I draw a picture. Here's my 283. Here's my 683. I want to find the area in the middle. Okay. Well, I have to standardize, but I have two numbers, so we'll standardize them both. So Z1 is going to be equal to X minus average over standard deviation. So it doesn't matter which number you do first. Let's do 283. Minus an average of 483 over a standard deviation of 100 equals -2. Let's do our second one. Again, X minus average over SD. So my second number I'm interested in is 683. So 683 minus 483 over 100 gives me +2. So now I have this picture. Here's Z equals +2. Here's Z equals -2, and I want the area in between. I can use the normal table, and I will show you how to do that in a minute, but you could stop and think and be like, wait, in this class, we have memorized, because we hear it over and over, and you're going to keep hearing it over and over for the rest of the semester, that if you're within 2 standard deviations of the average, that's going to be about 95%. So for a normal distribution, about 95% will be within 2 standard deviations of the average. So 2 standard deviations this way, 2 standard deviations this way. This has to be about 95%. Now, how would you use the normal table? Let's see what happens if you look up 2. So if I look up 2, z equals 2, it gives me an area of 97.72. But that's the area all the way to the left. So from here all the way over is 97.72. But that's not the area I want. I want the part in the middle. So you'll look up from -2 over. So -2 looks like we're at 2.28. And so this is the both areas to the left. How do you find the area in the middle? You subtract. So we'll do 97.72 minus 2.28 gives me 95.44. So it turns out for a normal distribution, within 2 standard deviations of the average is technically 95.44%. But that's much harder to memorize, so in this class we just memorize 95%. Let's see, in order to get into a certain males-only university, you have to score at least at the 80th percentile. So find a male's math SAT score that would be equivalent to the 80th percentile. So 80th percentile means you have 80% to the left. Percentile always tells you your percent to the left. So this is a problem where we have the percentage and we want to get back to our original x value. So we're working backwards. So we start at 80%, we go to our normal table and we look inside the percentages for 80%. So 80% looks like I'd be closest here to z equals 0.85. So I know my z value, but that's not really what I want. I want to get back to an x value. Well, remember, what does z tell you? Z literally says it's the number of standard deviations you are from the average. So on our cheat sheet, we have x equals our average plus z times our standard deviation. Now that's the exact same formula as what we're using up here. We just rearranged it so we can find x instead. So x is equal to our average, which is 483, plus z, which is 0.85, times the standard deviation of 100. So this literally says, here's the average, add on 0.85 standard deviations. This gives me 568. So if you want to be in the 80th percentile, you have to be at 568. Now the person who wrote this originally, she used the calculator. Her answer is slightly different because the calculator is slightly more accurate. So pick the closest value, 567. Okay, what's the percentile of someone who scores 520? This means, what is your percentage to the left? So our value is 520. I want to find the area to the left. So first let's standardize. Z equals x minus the average over the standard deviation. So our x value is 520 minus an average of 43 over standard deviation of 100 gives me 0.37. So basically I've rescaled now to z equals 0.37 just so I can use my table. So coming to my table, I look up z equals 0.37. Let's see, 0.37. My closest value here would be at the 0.35 for a percentage of 63.68. So 63.68. And that's the area to the left. I wanted area to the left, so I'm done. We're at the 64th percentile. Below is a table showing enrollment data for full-time undergraduate students. The class intervals include the left endpoint, but not the right. So for example, the class interval of 45 to 50-year-olds includes all 45, 46, 47, 48, and 49-year-olds. Basically, it's just a way of making sure we don't overlap our numbers. It doesn't usually come back to affect you too much. So we want you to construct a histogram. I am going to draw it here on the exam. I obviously can't have you actually draw it, but I could have you fill out a table like this on the exam. So you have each age, you have the percentage of people in that age. Now you need to come up with the width and height of an interval. So from the age 15 to 18, that's a gap of 3. You can find that by 18 minus 15, so my width is 3. But how will you find your height? Well, remember, we know that percentage equals height times width. Actually, I think we usually write width times height. Doesn't really matter. Which means if you want to rearrange and try and get h by itself, your height is going to be equal to, well, I divide both sides by my width. Sorry. And so your height is going to be equal to your percent divided by your width. So let's see, first one, for my height, my percentage is 1, my width is 3, so I'm at 0.33. Okay, next I have, let's see, what's my width? 18 and 22, that's a difference of 4. So my width is 4, so I have 68 divided by 4, which equals 17. And then 22 to 45, that's going to be a difference of 23. And my percentage is 29. So 29 divided by 23 equals 1.26. And 45 to 50, that's a width of 5. My percentage is 2, so 2 divided by 5 is 0.4. So draw our histogram, have your labels first. So down here is, what are we looking at? We're looking at their ages. And what are your units? It's ages in years. So for my vertical axis, it's always percent per whatever your units are down here. Our units are years, so it's going to be percent per year. I'm going to pick a scale. You would be more than welcome to pick a different scale. That's just fine. I'm going to start at 0, 10, 20, 30, 40. 40, 50. And over here, I'll do a scale of 2s. So my first category goes from 15 to 18. 15 to 18, I have a height of 0.33. So you can barely see it. My next one goes from 18 to 22 and a height of 17. That makes sense because you would expect to see a lot of undergraduates that are between 18 to 22. Okay, then I go from 22 to 45 and I have a height of 1.26. And I go from 45 to 50 with a height of 0.4. I didn't draw that far enough. Okay, 45 to 50 with the height of 0.4. Let's see. What were the units for the height of the interval? Okay, so height of the interval, that just means what are your units for your vertical axis. In this case, it was the percent per year. Then ask, are there more 19-year-olds or 30-year-old undergraduates? So basically, which bar is higher? So 19-year-olds, it looks like we have a height of 17. 30-year-olds, we have a height of 1.26. So there's going to be a lot more 19-year-olds. What percent of undergraduates are 35 and over? So again, we're just looking for the percentage, and your percent equals width times height. Let's see, but for 35 and up, let's see, we start at 35. It looks like we're going to have two different bars. So I'm going to draw this out. So we go from 35 to 45 with a height of 1.4. And then we have another one that goes from 45 to 50 with a height of only 0.4. Wait, was that the right height? Sorry, no, it was 1.26. So, and I'm going to basically add those together. So for my first one, I have a width of 10 from 35 to 45 and a height of 1.26. And my next one, I have a width of 5 times a height of 0.4, so it gives me 14.6%. Now, what percent of undergraduates are exactly 26 years old? This basically just means what is the height of that bar? Because our units are percent per year, so we want the year of 26, so we just look at the height at 26, and it looks like that's our height of 1.26. So about 1.26% of undergraduates are 26 years old. Number 6, some people think that drinking wine in moderation offers some protection against heart attacks. So a study examined 19 Western countries and found drinking more wine was associated with a decrease in heart attacks. Have the researchers shown that drinking wine prevents heart attacks? So this is one of the most important things we want you to take away from this class, is that you might find an association. You might find two things that seem to be related, but the problem is there are so many confounding factors, and it doesn't matter how hard you try to take out all the confounding factors. There are still confounding factors. And so when you just see something that says it's associated, that doesn't mean that you can say something else causes it. So association is not causation. There might be other confounding factors, so you cannot say drinking wine prevents heart attacks, even though you figured out that they were related somehow or associated somehow. So next problem. John works for a company that's debating giving company-wide raises. So one person thinks they should give everyone $100 more per month. What will this do to the average, to the median, to the SD? Well, adding the same number to each value in a data set, this is from chapter 4, means you will add that number to the average and the median. But the SD will stay the same, because basically if you had, a histogram, and I don't know what it looks like, maybe something like this, okay, and you add $100, it basically just shifts it all over. Nothing changes in the distribution, it just shifts it over. And so the standard deviation doesn't change, it doesn't get more spread out. Except it kind of looks like it did. So in this case, if we add $100, then we're basically just going to add $100 to the average and median, which makes sense. If everything is $100 bigger, you'd expect the average and median to get bigger too. But the SD stays the same. Now, one person thinks they should give everyone a 5% increase by multiplying each salary by 1.05. So what will this do to the average? What will it do to the median, to the SD? Well, it turns out that multiplying the same number to each value means you multiply that number to the average, the median, and the SD. So we will multiply the average, the median, and the SD by 1.05, or basically they all go up by 5%. And finally, here is a list of numbers. We're supposed to find the average and find the median. So your average, you always add them up and divide by how many there are. So we're going to do 4 plus 5 plus 1 plus 2 plus 8 plus 1 plus 6 plus 3 plus 9. And divide by how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. Please make sure you double check when you do this on the exam. So when I added them up, I got 39, and then I counted that they're 9, so 39 divided by 9 is 4.33 for my average. Now for the median, your first step is you have to put them in order. You cannot find the median if you don't put them in order. Okay, let's see. Looks like I have 2 1s, and a 2, and a 3, and a 4, 5, 6, 8, 9. I really like crossing them off. That way I make sure I don't miss anything, because that happens quite often. Okay, now you need to figure out where the middle is. To find the middle, I usually just start crossing them off for the top and bottom. So bottom, top, bottom, top, bottom, top, bottom, top. And it looks like I ended up with a 4 right in the middle. So my median is 4. Now let's say I had an even number and I didn't, let's see, what if even number of data? So let's say, let's pick a different color here, that I had 1, 2, 3, 4, 5, 6, and 8, and I wanted to find the median. Well, then I'd start crossing them off. 1, 2, 3, 4, 5, 6. Oh, look, I have 2 numbers. Well, which one is actually in the middle? If you don't know which one's in the middle, like this, you're going to take the average. So we'll do 3 plus 4 divided by 2, so 3.5 would be the median. So that's what you do if you have an even, just in case that's what you get on the exam.